Hi, my name is Sarah Ballesteros, and this is my Physics 2211 Lab 5, Falling Slinky. The purpose of this lab was to choose your own topic to use the tools and methods that we've developed in lab and lecture this semester and apply them to a complex physical system. It was also to observe and model the motion of a falling slinky being dropped from static equilibrium. We wanted to find out if the bottom remains motionless or not. We compared the observed data to predicted data, and we used GlowScript code. We also utilized Newton's second law to estimate the position and forces acting on the slinky. For the formulas used, we used Newton's second law, which is that force is equal to the change in momentum over change in time. From this, we have the position update formula and the velocity update formula. For forces, gravitational force is equal to mg times j hat. The tension force is equal to the magnitude of gravitational force in this scenario, and then we have the equation for drag force. F net is equal to mass times acceleration, or mass times the derivative of velocity. For constant versus non-constant net force, when velocity is constant, the net force is also constant. But when velocity is not constant, F net is non-constant and does not equal 0. Here's the tracker video showing the falling slinky. Then we use GlowScript to model the same scenario. We also for the code, we started with initial conditions and constants. We wanted to establish the system, which is our slinkies, initial mass, initial position, and initial velocity, all gathered from the tracker video, and then the size of the time steps. We looked at the gravitational force, and B, which is the proportionality constant for the magnitude of drag force, which we calculated through trial and error. Additionally, here we made the loop using the time before the top of the slinky reaches the bottom. In this loop, we calculated the force of tension of the slinky, which is just the opposite of gravity, the weight force, or the gravitational force, and then we used F net to calculate the slinky's new velocity and positions with the update formulas. And then we do the same process, obtaining the ball's position throughout the loop. In comparing our results, we see that the model and the observed position from the tracker follow very similar paths of position. In the first part of the graph, at the bottom of the slinky does stay stationary until the top reaches the bottom. The positions only start to vary after this point, likely due to error in my tracker points or a calibration error. I'd also like to point out that what this graph is showing, which is only the position in the y direction and only the position of the bottom of the slinky, our tracker position also likely has fluctuations due to external forces not accounted for in our computational model, but from real life. Now for our analysis, why does the slinky act like this? The net force remains constant until the bottom and the top of this slinky meet. The bottom of the slinky is motionless. It started at rest and stayed at rest until the net force was no longer 0. When the bottom of the slinky is stationary, the force of tension and the force of gravity have an equal magnitude, resulting in F net equal to 0. When the bottom begins to move, drag force and the force of gravity act on the system. At this point, there is no more tension force. What if the slinky were to be dropped on a planet with a different gravitational force? Would the bottom still appear stationary, and how would the motion of the slinky change in response to different gravitational pulls? If the slinky were dropped on a planet with a different gravitational force, the stationary effect of the bottom might change. On a different planet, the tension force and the gravitational force might not be equal and opposite in magnitude anymore. On a planet with weaker gravity, the bottom would likely stay stationary for a longer duration, while on a planet with stronger gravity, the bottom might begin to fall sooner as the tension would need to overcome a greater gravitational pull. Thanks for watching.